Chapter 3. Chapter 3 is about 1D steady state heat conduction. So it's a continuation of what we've learned in Chapter 2 and it sorts of blends in two concepts. In this particular chapter, we'll focus on how to solve 1D heat conduction equations in a solid, and I'll introduce the concept of thermal resistance and how to solve heat transfer through a solid using the concept of thermal resistance. So let's move on. What is thermal resistance? So every material resists the flow of heat, and the resistance depends on the material properties. That's the thermal conductivity or the heat transfer coefficient of the material. So if there wasn't any thermal resistance, you would have uniform temperatures everywhere. So there's a reason why one end of your pan is extremely hot and the other end is not so hot. And the reason is the material that's there. It may be your iron pan, so the iron resists the flow of heat, and that's why it does not allow the entire pan to be at the same temperature. So what it means that it takes time for the pan for the temperature of the pan to even out. So that's because of the thermal resistance offered by the iron pan, and the amount or the extent of thermal resistance depends on the thermal properties. That's the thermal conductivity or the heat transfer coefficient. So your air also offers thermal resistance and uh, resists the flow of heat. So we'll look more into that. So the concept of thermal resistance is analogous to electrical resistances, and they obey similar mathematical equations. So most of you might have learned electrical resistances and Ohm's law, and how electrical resistances or how to draw circuit diagrams in like different scenarios. So the basic concept of electrical resistance is that you will have a potential difference. So say the potential difference across a particular electrical resistance R elec is delta V, where V2 is smaller than V1. So we know that electricity always flows from a higher potential to a lower potential. So electric current is flowing from a higher potential to a lower potential, and it is resisted by a resistance R. And Ohm's law states that the voltage difference is equal to the product of the electric current into the resistance offered, or the resistance here is equal to the potential difference upon the electric current. In a similar way, we can represent thermal resistances as well. So let's say you have a certain body or a certain scenario where you have where you have two locations at different temperatures, T2 and T1, and T1 is greater than T2. Now we know that heat always flows from higher temperature to a lower temperature. So T1 has to be greater than T2, which is the case in the scenario, and there is some resistance or thermal resistance that's there between these two temperatures. Now this resistance can be due to conduction, due to convection, or due to radiation. So uh, we haven't really defined what kind of thermal resistance this is, but let's say it is some kind of thermal resistance, and the heat transfer between these two temperatures is Q. So similar to the Ohm's law, temperature difference delta T will be the heat transfer rate, not the heat flux, the heat transfer rate multiplied by the thermal resistance offered. Now this is analogous to the electrical circuits that we have, where your voltage is analogous to temperature. So your delta V is analogous to delta T. There you have a potential difference between 2 points or at 2 points, and here you have a temperature difference. And in for currents, the current flows from a higher potential to a lower potential. Similarly, heat will flow from a higher temperature to a lower temperature. Instead of electrical resistance, we here have thermal resistance, and this resistance can be uh, due to conduction, convection, or radiation. And obviously, instead of current, we have the rate of heat transfer. So it's exactly analogous to the electrical circuits or the electrical resistance that you've studied before. And the mathematical equations that are followed are also similar. So in this case, your Ohm's law was delta V equals to I into R, whereas for this case, for thermal case, you have a delta T which is equal to Q into R thermal, or we can say that the resistance is delta V by I. In this case, your thermal resistance will be delta T by Q. Okay, so this is the analogy between the two systems is very important to understand. It makes it easier to understand what's going on in different problems and then to formulate your mathematical equation. So let's understand this concept by taking an example of a plane wall, and let's try to draw the circuit diagram for this scenario. So let's say we have a plane wall. Let's say this is x is equal to 0 and x is equal to L. So the thickness of the wall is L, and let's say the surface temperature here is TS1. Surface temperature at L is TS2, and let's say we have cold fluid flowing on the right of the wall, and the temperature here is T infinity 2, and let's say we have a hot fluid flowing here, and the temperature here is say T infinity 1. Okay, and because it's a one-dimensional steady state conduction, let's assume that heat is flowing only in the x direction. So we have heat transfer rate in the x direction. So how will your temperature distributions look like? Uh, your temperature distribution within the wall will be linear, so something like that. And you will have a temperature distribution looking something like this right here, and something like this between TS2 and T infinity 2. So how many resistances do we have for the heat flow? So the two extremes that we see in this particular diagram or in this particular scenario are the T infinity 1 and T infinity 2. T infinity 2 is the hot fluid, so we know that T infinity 1 is greater than T infinity 2, which means that heat must flow from a higher temperature to a lower temperature, which is what we've assumed. Okay, so we have a resistance to the heat flow Qx due to convection in this region here. we have a resistance due to conduction. Sorry, we have a resistance due to conduction due to the thickness and the material of the wall. So let's say the wall has a thermal conductivity K, and let's say the fluids have heat transfer coefficients H1 and H2. Oh, let's take it the other way around. So let's say the fluid on the left has H1 and the fluid on the left has H2. And again, so the thermal resistance offered by them will be different. So let's say the thermal resistance on the left is R convection 1 and on the right is R convection due to convection 2. Okay, so now this is the scenario that we have. Now how will our circuit diagram look like? So anytime you draw a circuit diagram for a thermal system, the first thing you must identify is see the direction of your flow. So it will always be from a higher temperature to lower temperature. The second thing is identify if the system is in series or parallel. So I see that you have the convection, you have the resistance due to convection first, then the resistance due to conduction, and then the resistance due to convection, and I don't see any resistances offered in parallel. We will be doing a problem on that as well, but in this particular scenario, our resistances are in series, so they are in series. Okay, so it helps. So when you have this, the first thing that you must do is always uh, have the two extremes drawn. So let's say these are our two extremes, T infinity 2 and T infinity 1. Okay, then draw the temperatures that you know. So we know the surface temperature. Okay, it's not aligned. So we know the surface temperature here is Ts1, surface temperature on the other surface is Ts2. Okay, and then there's a resistance between Ts1, T infinity 1 and Ts1. There is a resistance between Ts1 and Ts2, and there is a resistance between Ts2 and T infinity 2. And what are these resistances? It's due to convection here, due to conduction between S1 and S2, and again due to convection between Ts2 and T infinity 2. And the direction of heat flow is from T infinity 1 to T infinity 2. Now, because they are in series, as we know from the electrical circuits, when electrical resistances are in series, your current flowing across each resistance is equal. Similarly, in this case, we'll have equal heat transfer rate across each resistance. So what that means is that our Qx will be equal to Q convection will be equal to Q conduction will be equal to Q convection from the other surface. Now let's write down the formulas. So let's say this is H1A into T infinity 1 minus Ts1 equals Fourier's law. So Ka, now A is the area of the surface. So this area right here is A. It will be Ts1 minus Ts2 by L. This is the approximate formula for of the Fourier's law. And on the other surface it will be HA into Ts2 minus T infinity 2. Okay, so we have this. Now I can write this down as H1A into delta T, say 1 equals to Ka by L into delta T2 equals to H2A into delta T, say 3. Or let's write it down so that it resembles like Ohm's law. So I'll write this down as delta T1 divided by 1 upon H1A. I'll write this down as delta T2 divided by L by Ka and delta T3 divided by 1 by H2A. Okay, so from Ohm's law, what was our Ohm's law? Our Ohm's law for thermal resistance was that our thermal was equal to delta T by Q, right? So let's see what thermal resistance we get here. So by comparing this, we can say that for convection or our convection in this case, if our uh, convective heat transfer coefficients would be equal, will be 1 upon HA, and resistance due to conduction for a wall, for a plane wall, will be L by Ka, where L is the thickness, A is the area across which heat transfer takes place, and K is the thermal conductivity. And this here is a general formula for plane wall. Okay, so this is how we understand a problem, draw the electrical circuit for it, and identify the thermal resistances in the system. Okay, so in our case we'll have two resistances which are due to convection and one resistance which is due to conduction. Now what will our thermal resistance or a total thermal resistance be for this system? So it will be uh, the addition or the combination of all the resistances that is there between T infinity 1 and T infinity 2. So our Qx will be the delta T between 2 and 1 or 1 and 2 divided by the total thermal resistance, or we can write this as T infinity 1 minus T infinity 2 divided by R total. Okay, so since these resistances are in series, we can just total them up. So you can write R total as summation of all the resistances, which is resistance due to convection on the left side of the wall, resistance due to conduction of the wall through the wall, and resistance due to convection on the right hand side of the wall. So here I've assumed that H1 is equal to H2 just for simplicity, and it must be noted that if you see these values, the values of the resistances, you can see that as the values of H and K increase, the resistance to the flow of heat decreases. So As your H and K increase, your denominator will go up and your overall resistance value will go down. So what does that translate to? It translates to that if you have higher values of H and K, the heat transfer rate will go up. So you will have faster heat transfer through your material. Now what that means is that if you have an insulator or say if you have insulation to your thermos or insulation to your house, those materials will have a very low thermal conductivity or heat transfer coefficient, which means that they will have a higher resistance towards the heat flow, and that's why they will not allow the temperature at one end to rise or drop with respect to the other end. So that's why, because you have a you have a material with low thermal conductivity or heat transfer coefficient between the walls of your thermos, that's why your coffee inside a thermos will stay warm for a longer period of time.